Hi, welcome to Physical Science, Unit 1 on Motion. This is 1.4, Newton's Law of Universal Gravitation. So first, let's identify some questions. If the planets are orbiting the sun, what force is holding them there in orbit? What force keeps the moon in its orbit? And could the force of gravity be universal? Newton's Law of Universal Gravitation says that if the apple was attracted to the earth, are all objects in the universe attracted to each other in the same way that the apple was attracted to the earth? And the answer is yes. Every object with mass attracts every other object with mass. Newton realized that the force of attraction between two massive objects increases as the mass of the objects increases and decreases as the distance between the objects increases. So first we need to get into some scientific notation. Scientific notation is really just a short way of writing really, really big or really, really small numbers. This is 5 and 12 zeros, and it can be written in scientific notation as 5 times 10 to the 12th. Or, similarly, this is 10 zeros and the number 3, a decimal place, and 10 zeros and the number 3. Can be written as 3 times 10 to the negative 11. You will use the caret button or the to the button or the y to the x button in order to get that exponent on your calculator. On your formula sheet, you want to have two boxes for the law of universal gravitation. The original equation says F is equal to big G m1 m2 over r squared, where big G is the gravitational constant. The gravitational constant that Newton discovered is actually 6.67 times 10 to the negative 11th. M1 and M2 are the masses of the two bodies in kilograms, and R is the distance between them in meters. That should go in box 1 on your formula sheet. F is the force in newtons. That should go in box 1 on your formula sheet. In the second box on your formula sheet, you need the original equation. F is equal to G m1 m2 over r squared. You'll use that equation to find force in newtons. R is equal to the square root of G times m1 times m2 all divided by F. You'll use that to find your distances in meters. M1 is equal to FR squared divided by GM2. You'll use that to find a mass when they're not the same. And M is equal to the square root of FR squared over G. You'll use that equation to find mass when they are the same. This should go in the second box you have labeled for Newton's law of universal gravitation. The law of universal gravitation is an inverse square law. If the distance doubles, the force actually drops by a fourth. If the distance triples, the force drops by a ninth. And if the distance is multiplied by 10, the force is divided by 100 because it's an inverse square law. The gravitational force exerted by a uniform sphere on a particle outside of the sphere is the same as the force exerted by the entire mass of the sphere were concentrated on its center, meaning that the force that mass 1 exerts on mass 2 is equal and opposite to the force mass 2 exerts on mass 1. The forces form a Newton's third law action-reaction pair. So any two objects, believe it or not, attract each other with a gravitational force proportional to the product of their masses and inversely proportional to the square of the distance between them. The force acts in the direction of the line connecting the centers of the masses. Newton discovered that gravity is universal. Everything pulls on everything else in a way that involves only mass and distance. This video explanation is going to be given in a different link. I'm going to show you a simulation at the end of this video that you can actually use to help you. But this is an image of the simulation. You'll notice that you have two spheres. You have a ruler to measure the distance between them. The force is given on both of them that will be the same, is given in scientific notation and in newtons. You can set the masses, and you do want to be sure that you have scientific notation turned on. So here's an example of the kind of calculation you're going to have to do. Jimmy is attracted to Betty. Jimmy's mass is 90 kilograms and Betty's mass is 57 kilograms. If Jim is standing 10 meters away from Betty, what is the gravitational force between them? Remember that force is big G times m1 times m2 divided by r squared. So you would literally take 6.67 times 10 to the negative 11th times 90 times 57 divided by 10 squared. Plugging that into a calculator, believe it or not, would give you 3.42 times 10 to the negative 9th. You're going to want to practice this before you have the assignment. Example 2, the moon is attracted to the earth. The mass of the earth is 6 times 10 to the 24th kilograms, and the mass of the moon is 7.4 times 10 to the 22nd kilograms. If the earth and the moon are 3.45 times 10 to the 8th meters apart, what is the gravitational force between them? Remember, Fg, the force of gravity, is big G, m1, m2 divided by r squared. So that calculation would be 6.67 times 10 to the negative 11th times 6.0 times 10 to the 24th times 7.4 times 10 to the 22nd, all divided by 3.45 times 10 to the 8th squared, giving you a force of gravity between the Earth and the Moon of 2.49 times 10 to the 20th newtons. A planet has a radius of 35 kilograms, 3.5 times 10 to the 6th meters, and a surface gravity of 3.8 meters per second. What is the mass of the planet? Again, use a second mass of 1 kilogram. So mass is force r squared divided by g m1. This would be 3.8, that's the force, times the radius squared, 3.5 times 10 to the 6th squared, divided by big G, 6.67 times 10 to the negative 11th, times 1, giving you a mass of the second object as 6.98 times 10 to the 23rd. Example, problem 1, two spheres of mass 35 are 60 meters apart. What is the force of gravity between them? Remember, F is equal to G m1 m2 divided by r squared. 6.67 times 10 to the negative 11th times 35 divided by 60 squared will give you a force of 2.26 times 10 to the negative 11th newtons. And problem 2, two spheres of mass 3,500 kilograms have a force of gravity of 9.6 times 10 to the 12th newtons. How far apart are they? This is the radius, or the r equation. R is the square root of g m1 m2 divided by f. So that this would be 6.67 times 10 to the negative 11th times 3,500 times 3,500 divided by 9.6 times 10 to the 12th, giving an answer of 9,225.6 meters. Thanks for watching. So this is a small little how-to video on using the simulation from today's assignment. Be sure that you turn on scientific notation. You're going to set your two masses. So for example, What is the force of gravity between a mass of 100 kilograms and 400 kilograms when they are 6 meters apart? So to measure them, you would just move the ruler up. Be sure that you're on 0, not on the end of the ruler. 6 meters. The force of gravity between them would be 7.42 times 10 to the negative 8th. It's as simple as setting all of your parameters based on your problem and then reading the answer off.